Hey, this is Dr. B, and this is the story of Bohr's epiphany. Around the early 1900s, it was beginning to become understood that certain things that are very small in nature are quantized. For example, energy was quantized. Planck's constant determined this. There are individual particles of energy for which you cannot go any smaller. Similarly, people were taking a close look at the hydrogen atom. And if you take hydrogen gas, run a little current through it, you will ionize that gas, turning it into a plasma. And if you take that plasma and simply put it through a prism to take a look at the wavelengths of light, you do not see a nice continuum from Roy to G to Biv going all the way to violet. Instead, you only see 4 sharp lines of light, suggesting that there's something about hydrogen that is similarly digital, quantized, if you will. And these numbers were studied, and back in the 19th century it was determined that there was a pattern to them. But to solve that pattern, you needed 2 whole numbers. We're going to call them inner and outer. And if you plug any 2 whole numbers into this formula, it will spit out an observed wavelength. It so happens that you need to have it end in 2 right here, so a quarter, in order to solve for these lines of light. Why don't we go ahead and do one? There's your units. Let's solve it for 3 to 2. So always make sure your inner number is smaller. So that's your 2 there. Put a 3 there. So it's a quarter minus a ninth. And if you chug that through, you'll solve this thing here. That means the wavelength of light in nanometers, which is what this is. Visible light being from about 400 to 700 nanometers. And you'll get 656. In other words, this red line here has something fundamentally to do with 2 whole numbers. Bohr realized this might simply be shells where the electrons are. Here's what it would look like when you go from 2 to 1. 2 being outer, 1 being inner. It simply goes down from there, releases some energy, and you could calculate it. It wouldn't be in the visible part of the spectrum, but it would be there nonetheless. Now, if this is really true, you should be able to calculate all sorts of different wavelengths, and you can. If you go from the first shell to the third shell, don't think that you will emit light, because that is absorption. But electron emission will happen anytime it cools down, so to speak, and goes from an outer to an inner shell. For example, 3 to 2. There's our 656 nanometers. We can do 4 to 2. There's your 486 nanometers right there. Teal sort of light, very pretty. And from 5 to 2, you can observe the 434. Perhaps that's the teal one right there. This is easy to replicate in a classroom. It doesn't require much equipment. And you can even do 6 out to 2 to get this violet light right there. So you should be, I hope, seeing that there's ample evidence that this shell model might be valid. Does it extend beyond red and beyond violet? You bet. They call these things like the Paschen series and the Lyman series. You just have to go to a different inner shell, perhaps the first or perhaps the third. But with this great body of evidence, this simple model for the atom where electrons reside in shells seems to have some validity to it. This is the story of Bohr's epiphany.